All right, how's it going, everybody? Back again for Recitation 6 for MAE 242, Intro to Fluid Mechanics. And this is posting a day late on Tuesday. Big storm came through Tempe and my power was out all last night. So, damn, that really sucked. But anyway, we got three problems here. The first two are going to be concentration of momentum, and the last one is going to be concentration of energy, which is fair game for your exam, so just a heads up on that. But this first one's just a really quick conceptual one. So in this figure, we've got a vane that's turning this water jet completely around, and we want to find an expression for the maximum jet velocity, V naught, if the maximum possible support force is F naught. And so this one, we're not even going to have to use any concentration of mass for this one. Usually mass and momentum are coupled. Usually need to do mass first to find whatever you need for momentum. But we're given an F naught, and we just want to solve for this V naught. Well, we know everything else we really need to about this, but oh, and do you like how I finally printed these bullshits out? It's pretty nice. I'm not drawing anymore. But first, I'll get some assumptions going. Just real basic. So we can say uniform flow. And say it's steady, inviscid, incompressible, of course. And we neglect pressure, right? All right, so now, like I said, we don't even need to do any concentration of mass. We're just going to go straight into momentum. So let's get our momentum equation going, right? This is the sum of the external forces. It's equal to the time derivative term, which will go away anyway, but whatever. Control volume, rho, v, dv, or, d volume, right? Plus the control surface term, rho v, v dot n, ds. So like I said, this term will go away anyway. And then on this left-hand side, this is all of your external forces. So like if we had pressure forces, that's where this would be. Or like body forces, right? Like gravity, stuff like that. But in this case, right, all we have is just this F naught over here. And let's make sure it's draw coordinates, because this is a vector equation, right? So it's a vector equation, so we need to actually break this down into components. It just so happens, right, that we have nothing going on in the y direction, so all we're going to be caring about is this x direction. So what's the only force in the x direction? Well, it's this F naught. And which direction is it pointing? Negative x. So we're going to have negative F naught is equal to, that went to 0, right? So now, for both of these inlets, right, it's just it's going to be 1D fluxes in the inlets, right? So it's just going to simplify down to your rho VA term, right, for this M dot. Or it'll be, rho VA, and then, when you get the other one in there, the other velocity, it's a V squared, right? Rho V squared A, whatever. So first off, let's look at this inlet right here, this one, okay? So let's get our control volume going. And I'm just going to draw the whole thing like that. That's fine. All right, here's our normal vectors right there. And the other one right there. Okay, for this inlet, all right, this inlet right here. So first, density is constant. That's totally fine. Now this first V right here, this first V corresponds to the actual velocity vector. Where is this velocity coming from? And which direction is it going, right? It's going in the positive x direction. So that's cool. It's just going to be V naught. Cool. Now this other V dot n, this is where you have to dot it with the normal vector, right? You have to look at it in relation to the normal vector. And when you dot these two vectors, you get a negative V naught, right? It's perfectly opposing it. Cool. And then this ds, right, it's just a cylindrical area. It's the area of a water jet. So I'll still just call it A for now. It'll be, d naught, pi d naught squared over 4, whatever. I'm just calling it A for now. Okay, cool. So done with that. Now let's go back up top, right? Came up through here. Now it's going out. So again, we have density, which is constant. That's still fine. Now again, this first v is actually where that velocity vector is going. So now, in the case of up here, it's going in the negative x direction. So we have a negative v naught. And then similarly, let's look at this v dot n. The velocity vector and the normal vector are in this exact same direction. So when you dot it, you get a positive 1, right? So boom, there's that. And then still have that a. So I like this problem because it shows you just because you have an inlet or an outlet doesn't mean it's always going to be positive or negative in the momentum equation, right? You need to really pay attention to where the stuff is pointing. So now, right, we've got negative f naught equals negative 2 rho v naught squared a. We're solving for v naught, right? So just keep solving. I'm gonna drop the positives, right? So we have f naught equals right, so it's like v naught is equal to root f naught over 2 rho pi d naught squared over 4. Cool. Easy enough, not too bad. Just quick little conceptual one that I've just been wanting to put on here for a while. The second one, you actually have to do some integrating, so that's pretty nice. Oh yeah, and you can simplify this however you want. Who cares? It's not that big of a deal. All right, now this next one, we have to do some integrating, so that'll be fun. So here we have an experiment to determine the force acting on an oval-shaped body. A model is mounted in the test section of a wind tunnel. The test section itself has rectangular cross-section with height 2h and width L into the page. The model spans the entire width of the test section. The model is subject to a steady, uniform, incompressible flow of velocity v1. The pressure gauge indicates a pressure difference, delta P, between the test section exit, location 2, and the test section entrance, location 1. The velocity profile downstream of the model is shown in the figure, and it's linear. You can see it's linear. Use the control volume shown. Find the force acting on the model in terms of given quantities v1, h, L, delta P, and density rho. So first off, I'm not even going to write the assumptions. It gives it right there. I'll say assumptions given. That's all you really need. Like if you're doing homework and like a test, please write these down, but just say given, cool, whatever. All right. And so first off, we need to get this velocity profile. We're going to call this v of h, or v of z, I guess. V of z, and you can see it's just a linear velocity profile where we know the maximum has to be at the edge. So how do you do that? Well, Vmax is going to be our scaling factor. And we want it to be linear with maximum at the edge. So we're going to be stepping with our z. Let's go z over h. Boom. Easy as that. Quick mental check. Well, what happens when z equals 0? Right? You get 0 at the center line. What happens when z equals h? You get 1. Vmax times 1 is Vmax. Boom. So there is our velocity profile. Literally easy as that. So now, all right, but we have this Vmax, and we're going to have to be doing some integrating to figure out all the math that goes on with like the conservation of mass and conservation of momentum, stuff like that. So we want to find what this Vmax is in terms of V1. So how do we do that? We'll do our conservation of mass. I'll do it right here, I guess. Right. So we have our 0 is equal to time derivative term right, and it's steady, so that goes away. So now here we have 0 equals, let's break this down, break it into the inlet. This inlet is easy enough, right? Here's our normal vectors here. There. So this inlet is just going to be negative rho v1 times, what's our area here? It's just going to be 2h times L. Cool. Now for the outlet, we're going to make a little shortcut so we don't have to like negative h to h. We're just going to break this thing in half and go 2 from the integral from 0 to h of rho times our Vmax z over h, and the velocity is constant into the page, so that L is going to be a constant, and then we're stepping with dz, right? So let's move this over. Ooh. Is equal to, let's pull out all of the constants we can. 2 rho Vmax 1 over h L. All right, and then go and compute out this integral. It'll be super easy, and you get a whole bunch of stuff to cancel. You end up getting Vmax is equal to 2v1. Pretty easy, you'll dot that. Then you want to plug this back into your velocity profile. So I have v of z is equal to 2v1 z over h, which is important. All right, so now we want to find the force acting on this model, right? So you can draw this force however you want. I'm just going to draw it like, I would call it FD, whatever. And here's our abscissa. It doesn't matter. Draw it if you want to draw it the other way. It doesn't matter. Cool. So now, if we want to find some force, we're going to have to do some conservation of momentum. So let's do that. Again, right, we can directly use this one now because we have everything in terms of what our given quantities are, our V1. So let's keep going. Got all right, where again, this time derivative term goes away. And now this external forces, right? So first off, we're going to have this negative FD, right? That's our main one we're going to be solving for. But now we also have these pressure forces we have to worry about, right? We know there's some delta P here from, P1 acting over here and P2 acting from over here, right? Obviously through the whole thing. But what is up? And for these, right, we don't care about, we're not dotting anything, right? Literally, what direction are these pressure forces acting? In the case of P1, right, it's just in positive direction. So plus FP1, and then opposite is true for the second one. Boom. Easy as that. And right, what's a pressure force? It's just pressure times an area. So I'll go and do that in a sec. But let's keep simplifying, right? And so again, for this inlet, it's easy enough. It's going to be negative rho V1 squared times A, or 2HL, whatever. Now again, we just have to do this double integral, right? This multiplied by 2, this integral. 2 times 0 to h of rho. And now we have to square this entire thing, right? So it'll be 4 V1 squared z squared over h squared. Again, we have L dz. Okay, so now let's keep simplifying. We've got negative FD. Again, like I said, these pressure forces, it's literally just pressure times area, right? So we're going to have plus P1, but we don't necessarily know P1 quite yet, but that's fine, times 2HL minus P2 times 2HL equal to negative rho. Again, let's bring out all of the stuff we can from here. And I'll leave you to go and do this integral. It's, again, it's super easy. It's z cubed or h cubed over 3 once you get all done with it, but whatever. the more important thing, so we've got this, literally, so if you go and factor out this 2HL, right? Literally, you'll have a P1 minus P2. That is, by definition, delta P. Boom. And now we have that in terms of what we wanted, right? On the left-hand side. So anyway, this all simplifies down to -2 rho V1 squared 2HL plus 8/3 rho V1 squared HL. Oh, there's an extra 2 in there. Whoops. Simplified too much. Anyway, so yeah, just keep going. We're just solving for this FD. Just go manipulate. We have everything we want now in terms of everything else, so just go and keep solving. You end up getting FD equals HL times 2 delta P minus 2/3 rho V1 squared. All right, and go simplify however you want. I factored out the HL, but I mean, not too much of an algebraic leap from there to there. Just go and do the math for it. It's not that big of a deal. But yeah, there's that. Yeah, whenever you're given some sort of delta P, right, that's a huge giveaway that you're going to have to do some conservation of momentum, right? Don't neglect that. That's a big thing. But yeah, always get your assumptions going. They were given in the problem, but of course, you know, if you have an exam, write them, all that stuff. Remember how to find some velocity profile, right? You know, it's going to be something in some form like this. Just make sure it matches your boundary conditions. Simple as that. And so now let's move on to problem 3, which is the tougher one. It's energy equation one, and energy equation problems aren't necessarily that hard, but they just have a lot more terms going on. So anyway, so in this one we have air entering this mixing device from ports 1 and 2, and exiting from port 3 at the conditions shown in the figure. So we have all of these flow rates, temperatures, pressures, diameters, all that stuff is given. The circular ports have the given diameters, whatever. Heating elements provide heat to the fluid at a rate of Q dot. So if you really enjoyed thermo, right, this is where your Q dot comes back in, your heat flow rate. 67 kilojoules per second, so that's, 67 kilowatts, I guess. In order to maintain the flow conditions at the outlet port 3, impellers stir the flow inside the chamber. Air-specific heat capacity at constant pressure is CP 1 kilojoule per kilogram Kelvin. All right, so now for part A, I'm just going to do like one of them, right? Wants us to calculate the densities at ports 1, 2, and 3. The specific gas tons for air is R equals 287 joules per kilogram Kelvin. So this one's easy, right? I'm not even going to define any stuff. Let's just go. Remember your ideal gas law, right? Ideal gas law. P equals rho RT. So rho equals P over RT, right? And so I'm just going to do rho 1, okay? So it's our pressure at P1. It's 140 kPa, so it's going to be 140,000 over R, it's 287. And then temperature, of course, temperature has to be in Kelvin. And so it's 273 plus 21, so 294. Nope, getting rho 1 is equal to 1.658 kilograms per cubic meter. All right, and you can go do the rest of them, right? It's fine. I'm just going to do everything symbolically anyway. But all right, so now we want to find the flow rate Q3 at the outlet, okay? And so let's define our control volume. All right, so we have a outflow here, and then all these. I'm just highlighting them a little better. These are not the normal vectors, right? The normal vectors are like that. Get the idea. right? But in this, we're given Q1 and Q2, and we need to find Q3, right? So, you know, concentration mass, and I'm not going to do the whole equation. I've already done it like 3 times. I'm just going to idealize it into m dot in equals m dot out, right? And remember, m dot is equal to rho times q is equal to rho VA, right? Because literally, that's that, right? And so, all we have to do here, right? We know, right? Let's just sub everything in, okay? So we have what's coming in. We have rho 1 Q1 plus rho 2 Q2 has to equal rho 3 Q3. Cool. And so from A, I'll say from A, the 2 density, or all 3 densities, or no. Say plug in. I mean, this is not the biggest deal in the world, right? Solve for Q3. Right, because we're given Q1, Q2, and we found all the different densities. We only have 1 unknown. Solve for Q3. Q3 is equal to 3.028 cubic meters per second. All right, and lastly, the actual big bulk of this question, right? Part C, find the power, W power, required to operate the device. All right, so C, we're gonna have to do our energy equation. Right, and this is in the form of Q dot plus W dot. So basically, the net heat flux plus the net work being done. And it just happens in this case, right? The only heat that's coming in is a 67 kilojoules per second. And then the only power being provided is by this WP, right? We'll call it WP up here. But this can be, you know, this is like shaft work. This can be, you know, viscous work. It can be, if you took thermo, you know, all the different ways of providing work. It's fine. It's equal to, as usual, in any sort of transport equation, we have the time derivative term, which will go away, but whatever. And this is really the only equation I don't have super memorized, because I just don't have to use it all that much, but it's density times, in parentheses, we have U hat, which is the specific internal energy, plus 1/2 V squared, which is the specific kinetic energy, plus GZ, which is the potential energy, specific potential energy, times, you know, and then have the dV term. Then we've got the control surface term, which again, we're going to have density out front. And again, we've got U hat. But now we have P over rho, which is just like the pressure component. Then everything else is the same. Now we have the V dot N ds. Cool. So basically the same vibe, just more stuff to have to deal with. So again, this goes away. And again, I'll just really scribble that out. And so this Q dot is only what's coming in through right here, right? And then the W dot, that's our W dot power we're gonna be solving for. So it really kind of simplifies pretty well. So Q dot plus W dot P is equal to all this stuff over here, okay? So I'm just gonna rewrite this. And I'm even going to rewrite this further and say, since everything is 1D inlets, right, this V dot N and this ds just simplifies to the velocity and the area, right? That's easy enough. So let's do it again. So you'll have the rho out front, and you'll have a U plus. Let's call that VA, right? And so the only really tricky thing, right, is, I mean, we could do something with this P over O, that's cool for each inlet and outlet, but the U hat, the specific internal energy, is kind of tricky to deal with. But we know from thermo that U hat plus P over O is equal to H hat, specific enthalpy, which is equal to Cp times T. And what are we given in the problem statement? We are given Cp, way up here, all of that. We're given Cp, and we are given all of the temperatures. So if you need, I'm not going to plug in a lot of numbers. This would take forever, and it's trivial. But, you know, first off, make sure you get this into joules, right, instead of kilojoules, but whatever. But we're given the Cp, we're saying it's constant, and we're given all the temperatures. So this actually becomes really, really easy. So again, now all we have to do is break it down for inlets and outlets and just plug and chug. So we're gonna have Q dot plus W dot P is equal to, I'm gonna write this out one time just because, so we're gonna have negative, right, negative rho 1, because that's an inlet, negative rho 1 times Cp T1 plus 1/2 V1 squared plus G Z. Oh, and also, right, we're dealing with gas. We're dealing with gases. I totally forgot about this. We're dealing with gases. So this GZ term goes away every time, right? So we don't even need it. So that makes our lives a lot easier. Plus V1A, which A is just, you know, pi D1 squared over 4, whatever. Now, same thing, minus rho 2 and then plus rho 3. Right? And so now, I guess the only thing technically we don't know is the V's, right? But for velocity, Q equals V times A. So V equals Q over A, right? Where we know all the Q's at this point and we know all the areas. So go find your V's from that. So anyway, we end up we're solving for this W dot power, right? W dot P. So W dot P is equal to negative Q dot minus, and I'm not going to do the full thing. I'm just going to write parentheses, right? But whatever. Minus rho 2, all of that stuff in there, plus rho 3, all of that stuff, right? You know, all of these terms, whatever those work out to be, right? It's just plug in the numbers. It's not that big of a deal. So anyway, plugging in all that stuff, right? Make sure you get this into 67,000 instead of 67 kilojoules. Get it into joules. Just keep solving, whatever. W dot P should be equal to negative 117,700 joules per second, which is equal to negative 117.7 kilowatts. Cool. And that is pretty much it. But again, really, I mean, like, there's more stuff you have to deal with the energy equation, but it's really nothing super, super hardcore. That's the thing about all of the conservation of mass, momentum, energy stuff. It's all the same concept. You're just riffing off the same concept. But, you know, for energy, you'll definitely have to get a little bit more thermo vibe going to it. But again, not the biggest deal in the world. If you have any questions, of course, let me know. Drop in the comments or shoot me an email. But that's about it. Thanks, guys.